And one of the questions we're going to ask is, what is the angle between these cables? So I'm actually going to leave this problem and talk about the dot product first. And then in a separate video, we'll actually work this problem. But once we write this vector and this vector, we're going to use the dot product to find this angle. So the dot product is one way of multiplying two vectors. If you have a vector A, which we'll just say is equal to 1, 2, 3, and let's just say this is pounds. And we have a B vector, which is 4, 5, 6, and we'll just say that's pounds. And if I tell you, let's dot A, dot B. The formula, if this is AX, AY, AZ, and this is BX, BY, BZ, then to evaluate the dot product, you go AX times BX plus AY times BY plus AZ times BZ. So 1 times 4 plus 2 times 5 plus 3 times 6 is 4 plus 10 plus 18, which is 14 plus 18, which is 32. Notice that this is a scalar. It's a single number, so the result is a scalar. This is sometimes called a scalar product, vector product, because the result is a scalar. Here I showed you how to evaluate it by hand, but actually your calculator has a dot product function in it. And so if we actually go to your nSpire and look in the catalog, we're looking for D, we're looking for dotP. So there's dotP. So hit enter, dotP. And so we're going to enter the first vector. And so we're going to go to control square bracket. And we're going to go 1, comma, 2, comma, 3. Step out of that bracket, put in a comma. And then we're going to enter the second vector, control square bracket. And this is 4, comma, 5, comma, 6. So it's the format dotP, A vector, comma, B vector. And you're basically telling the calculator, evaluate the dot product of these two vectors. And so if you hit enter, you get 32. And so with super easy numbers, this is easy. But actually, if you've got two pretty weird vectors in 3D, using the calculator is great. So that's the dot product, evaluating that. So that's how you evaluate it. So what do we use the dot product for? So we're going to use it for two different things. One is the angle between two vectors. And so if you have a vector A and a vector B, and you have an angle theta between them, the magnitude of A dot B, we define that as AB cosine theta. So where A is the magnitude of A, B is the magnitude of B, and theta is the angle between them. So if you're looking for this angle, then you can say cosine of theta is equal to A vector dotted with B vector divided by A magnitude divided by B magnitude. But if you look at this A vector over A magnitude is a unit vector of A. And the B vector divided by the B magnitude is the unit vector of B. So the angle theta between these guys is equal to the unit vector of A dotted with the unit vector of B. And that gives you that angle. Pretty cool, pretty helpful. Another thing we're interested in is the projection of A onto B. And there's two ways to get that, to get the projection. So we're looking for this F projection. You might also call that F parallel. Well, the F parallel or the F projection is equal to A cosine theta, if you know theta. So if you already found theta from here, then the A projection is just equal to the A magnitude times the cosine of this angle. If you haven't found theta yet and you're wanting to find it directly, if you come back to this formula where A dot B is equal to AB cosine theta, the projection is A cosine theta. And so if you look at this formula, to get A cosine theta, we divide both sides by the B magnitude. And so A cosine theta is equal to A vector dotted with a B vector divided by a B magnitude. But the B vector divided by the B magnitude is the unit vector along B. And so the A projection, you can dot it with the A vector dotted with the unit vector B. But again, I think it's just easier to get the angle between the two and then just get A times the cosine of that angle. Either way, you get it. One last thing I'll mention to you is if this is a projection magnitude, what is a projection as a vector? So the A projection acts along B. So his direction is the unit vector of B. So his magnitude, we saw, his magnitude is A vector dotted with UB. And again, that's a scalar. That the result of that is a scalar. And then you multiply that number times UB, and that gives you a projection as a vector. And then finally, if you want a perpendicular, so the presence of an a projection, or what I would call an a parallel, implies that there's an a perpendicular. Well, a projection is a vector plus a perpendicular is a vector is equal to the a vector. And then finally, the a perpendicular as a vector is equal to the a vector minus the a projection as a vector. And you can get a projection as a vector, or I'm sorry, a perpendicular as a vector. You can also get a perpendicular is just equal to the a magnitude times the sine of theta, which is what you found. So it's easy to get a projection as its magnitude. Getting his direction is a little harder, but writing the B vector or the A projection vector and subtracting that from the A vector will give you this guy as a vector. This sounds confusing, but what you really should do, if you're dedicated to being a good static student, is every time I work a problem like this, even though I know this stuff, I basically will write this out. I'll draw this picture, an A vector, a B vector, an angle. And I'll write A dot P is equal to AB cosine theta. And then I'll do this math, and I'll get the theta is equal to the inverse cosine of unit vector of A dotted with unit vector of B and the projection. So I will literally write this out every time I work a problem like this, just to remind myself of it. And keep in mind, to be a great static student, you should be keeping a notebook or a collection of these pages. And for each class of problems that we work with, you should write out the basic formulas, write out the key ideas. I mean, when you come back to this sheet here, you should rewrite this sheet in your own way, just to cement it into your brain so that you know it, that you know it, that you know it, that you're not guessing. You're not going, what kind of vector is that again? But you go like, okay, I know that's a spherical coordinate, and you know how to enter it into your calculator. So you should be writing these out on your own. So that's dot product. We'll close this video here, and then we'll work a problem using this.